morning, good evening, good afternoon, everybody, wherever it might be. Today we have double hosting. It's both from Warsaw and from Morelia. I understand that with you, Francesca, is Elmar, right? And how about Atul? Atul is also there?
Yeah, on Iraq, yes.
Okay, so there are three of you in Morelia, right?
Yes.
Okay, good. So today it's Francesca and Andrea on Amplified Graph System Algebras as course of Cuntz-Krieger Algebras. Francesco, it's all yours. Take it away.
Thanks, Piotr. Okay, so yes, today I'm going to talk about a joint work with Sophie Ziegers, which appeared on Archive yesterday, basically. And so how is the audio? Can you hear me? Is it fine?
Yeah, I can hear you loud and clear. Perfect.
Okay, yes. Perfect. Okay, so it has some connection with the talk by Elmar last week, meaning that in the first part of the talk, I'll try to explain some general theorem which is motivated by examples, of course, by some examples we are interested in. And then in the second part of the talk, I'll give one example in particular, which is the Grassmannian 2-4, and which is what also Elmar talked about last week. I will tell you how you can apply this stuff to the study of this Grassmannian. So let me start from the beginning. Let me recall the basic definition. By a graph, here we mean a quadruple, E0, E1, S, and T. E0 and E1 are just sets of any cardinality, so they can be infinite sets, they can be even uncountable. S and T are two maps from E1 to E0. Elements of E0 we call vertices, elements of E1 we call edges, and S and T are called the source and target maps. So they tell you for each edge what is its source and what is its target. On the right, you see a picture that I have shown in probably in many of my talks. This is just to show what can happen with these graphs. You can have basically anything. Okay, in this example, I have finitely many vertices, but still it shows you that you can have parallel edges, multiple edges from one vertex to another, edges going in opposite directions. You can have cycles, loops, even multiple loops attached to the same vertex, and so on. Okay, so as I said, E and F have E0 and E1 are sets of any cardinality, but then in my examples, and not only in my examples, even in the theorem, E0 will be finite and the E1 will be at most uncountably infinite. Okay, so a vertex V in E0 is called regular if here S minus 1 of V is so the preimage using the source map of V. This is the set of edges which start at V, and this set should be finite and non-empty. If this happens, we say that the vertex is regular. So the vertex emits finitely many edges and at least one. If it is not regular, we call it singular, and what can happen for a singular vertex is that either the set of edges emitted from V is empty, and then we call it a sinc. So in this picture, this vertex denoted by V is, I think you don't see my laser pointer for some reason, or there is a huge delay, but anyway, so the V, the vertex denoted V in the picture is a sinc, it emits no edges. Another thing that can happen is that a vertex emits infinitely many edges, and in this case we call it infinite emitters. So these are the two types of singular vertices. This is now the next notion. This is the definition of one of the terms that you saw in the title, which was on amplified graph system algebras as course of Cuntz-Krieger algebras. So this definition, I think it was given for the first time. So this term was introduced by Soren, Ehlers, and Efren Ruiz, maybe, and somebody else. There is a paper called amplified graph system algebras. And so a graph is called amplified if given any two vertices, the set of edges that start at the first vertex and end at the second vertex, this is either empty or an infinite set, countably infinite. So between two edges, you either have, between two vertices, you either have no edges at all, or you have countably infinitely many. Okay, so this is one of the terms that appeared in the titles and is one of the class of graphs we are interested in. So let's see some examples. In this first example, you see a graph which consists of a cycle. A cycle means that if you start from a vertex and move following in the graph, following the direction of the edges, you come back at the point you started from. Here in this second example, I changed the direction of the bottom arrow, and now you see that the bottom right vertex, this is a sink, and from this vertex, there is no way to go back to any other vertex by following the direction of the arrows. So this is no longer a cycle. This is a graph with a cyclic graph. So a cyclic means that it has no directed cycles. If you forget about the direction of the edges, this is a cycle, but undirected. And when I say cycle, I always mean a directed one. So for me, this is an example of a cyclic graph. So in the next example, I take the second graph, I replace every edge by uncountably infinitely many, and now this is an example of an amplified acyclic graph, and this is the graph of the class of graphs we will be interested in. Okay. Now that we recalled what we mean by a graph, let's see the definition of a graph C-star algebra. This is a definition / theorem because I'm going to define something using some kind of universal property, and then you have to show that this something exists, but it does. This is a theorem. So if you have any graph denoted capital E, it's graph C-star algebra denoted C-star of E. This is the universal C-star algebra, which is generated by two sets of generators. One set is a set of projections, one for every vertex. So for every vertex V, you have a projection PV, and this projection should be mutually orthogonal, meaning that if you multiply two of them, you get a 0. Then you have another set of generators, one for each edge. For each edge E, you have a partial isometry denoted by SE. These partial isometries also should be mutually orthogonal, by which I mean that the ranges are mutually orthogonal. And you have some relations. These are denoted CK1, CK2, CK3, where CK stands for Cuntz-Krieger. For every edge E, SE star SE should be equal to the projection of the target vertex of E, T of E. SE star should be less equal than the source, than the projection of the vertex source of V. And then if V is a regular vertex, so meaning that the set S-1 of V is non-empty and is finite, then if V is a regular vertex, the next relation tells you that the sum over all edges emitted from V of SE star is equal to PV, to the projection of V. So if the vertex is regular, the relation CK3 implies CK2. So CK2 is not necessary for regular vertices. So if the source of the edge E is a regular vertex, so if the source is not an infinite emitter, then CK2 follows from CK3. Otherwise, this is an additional condition that you have to impose. So another observation, maybe another thing that I should say is that the second condition is the only one which is not an algebraic condition, but you can reformulate it in an algebraic way. You can, this is equivalent to saying that P source of E multiplied by S of E from the right, this is equal to S of E. So you can rephrase it in an algebraic way. Okay. So these PV, these projections, if you take the sum of all these projections, this is a neutral element, a unit for the multiplication in the graph C-star algebra. But of course, you can sum over all vertex projections only if you have finitely many vertices. So in particular, the graph C-star algebra is unital if and only if the set of vertices is finite. And there is a canonical action of the group U1 on a graph C-star algebra, which is called the gauge action, an action by automorphism. And this is defined on generators by the following formula. So projections are invariant under this action. A partial isometry SC, if I act with a unitary element U, becomes U times SC, and the adjoint SC star becomes U star SC star. So in particular, this means that if you consider the zeta grading associated to this U1 action, projections have degree 0, this partial isometry SC have degree 1, and SC star has degree -1. And this defines your grading, your zeta grading on the graph C-star algebra. Okay, not only the action induces a grading, you can transform it into a coaction of the commutative quantum group C of U1. And okay, sometimes it's useful to have a coaction instead of an action. The degree 0 part of this graph C-star algebra, which means the set of all the elements that are invariant under the gauge action, this is called the core of C-star of E, and it will be denoted by this symbol that you can see in the yellow box, C-star of E with subscript U1.
Sorry,
Okay.
Francesco, I have a stupid question. I don't see the axiom that if you have SF star as E at 0, as long as E is not equal to F. I know we can prove it if you are row finite, but you're not assuming row finite.
What condition, sorry?
SF star times SE is equal 0 if F is
Yeah,
different.
no, but this is what I said. This is the condition that the partial isometry are mutually orthogonal. So it's written in word, mutually orthogonal partial isometry means this. But one has to be careful, you are right, because this is a condition that sometimes even I forget when I check that a star homomorphism is well defined. So that is an important condition which is not automatic, is the orthogonality of these partial isometries.
But you see, here's the wisdom of defining it through Levi-Pav algebras. Then things are completely clear. You don't need this ugly CK2 because it is an ugly condition. You can write it as an equality, and it's much easier to check. And then when you know that you come from Pav algebras, all these things I'm asking about are completely trivial. You just add two Cuntz-Krieger relations and you're home. Why do
this is true. I mean, it is much more clear, but it is longer. This is the short version to introduce I mean, you just save some time if you introduce graph algebras in this way. But yes, if you start from Levi-Pav algebras, all the conditions are algebraic and are more clear, easier also to understand.
I'm not sure that confusion saves time. I'm not sure. Anyway, go ahead.
Okay. Anyway, so let me give some elementary examples. So elementary examples, in this first example, you have the graph consisting of one vertex and one loop. This means that you have a single generator, which is the partial isometry S attached to this loop. And the two conditions, CK1 and CK3, tells you that SS star and S star S are both equal to the vertex projection. Since there is only one vertex projection, this is the unit element of the C-star algebra. So what you get is that this S is a unitary, C-star of E is the universal C-star algebra generated by a unitary, so it is continuous functions on the circle. And this is the first example. So second example, this is still elementary, but a bit more interesting, and it has something to do with what I'm going to talk about later. Here you have two graphs. Capital E has two vertices, one loop and one arrow from the vertex supporting the loop to the other vertex. I'm going to call E1 and E2 these two arrows. Capital F has two vertices and countably infinitely many edges from one vertex to the other, and I call these edges F0, F1, F2, and so on. And so what are these two guys? So it is not difficult to show that C star of E is isomorphic to the Toeplitz algebra. In fact, the isomorphism is the map which sends the unilateral shift, the generator of the Toeplitz algebra, to the sum of the partial isometries of these two edges. And then it's not difficult to show that it is really an isomorphism. You can explicitly construct its inverse, check them that they are both star homomorphism, and so on. So the second graph, C star of F, the graph C star algebra, this is the minimal unitization of the compact operators. And also here everything is explicit. You can send each partial isometry attached to these arrows. You can send to an infinite matrix, to a matrix unit. So an infinite matrix which has only one element equal to 1 and everything else equal to 0. You have to choose in the correct way these matrix units, but it's not difficult to write down the explicit isomorphism with compact operators. And you get the minimal unitization because the sum of the two vertex projections, this is the unit. So you have finite rank operators, the closure plus the identity on L2 of L. Okay, what is more important, the reason I am showing this example is that this is one of the examples where you can construct explicitly a star homomorphism from an amplified graph C star algebra to the graph C star algebra of a finite graph. So E is our finite graph, F is our amplified graph, and you have an embedding phi of C star of F in C star of E. This is defined on generators as follows. Here I denote all the partial isometries generated by a graph C star algebra by the same symbol S, but then the edges are denoted differently. So by looking at the edges, you should understand this isometry to which C star algebra belong. So I think the notation is not too confusing, but if it is, you can just ask me. So anyway, so this embedding phi sends the isometry S of Fn attached to the Rfn of the amplified graph to the partial isometry associated to the path that does n loops around the first vertex in E and then goes to the right. So here you have SE1 to the power n, S of E2. So this is, you can prove using some general theorem that this is an embedding, and it is not U1 equivariant. So if you want to prove injectivity, you have to use the version of the gauge invariant uniqueness theorem, the version where you have loops with an exit, where every loop has an exit, okay? And the important thing is that, so this is an example of embedding of an amplified graph C star algebra into the C star algebra of a finite graph. This is not exactly what I'm interested in because, so see, the image is not in the core. The image, these elements in the image are not U1 invariant. So what I'm interested in is embeddings where the image is the core of the C star algebra of some graph E, and in particular I would like this embedding to be an isomorphism with the core. So why this? The reason for this is our next example, class of examples. These are the examples that motivate the general theorem that we proved in this preprint. Okay, so the motivating example, I think I gave many talks about this class of examples, but anyway, these are odd dimensional quantum spheres. There are many quantization of spheres that one can study, those related to Q deformations. These are the ones I'm talking about. Then you have multi-pullback quantum spheres. And there are also other examples like theta deformations coming from twists and so on and so on. So I say quantum sphere, but I should be more precise what I mean. I mean this coming from Q deformations. And let me recall you, so let me give you some reference to recall you where these things come from. So these, in general, these quantum spheres were introduced in the 90s by Waxman and Soibelman, and they were introduced as quotients in some sense. So the starting point is the quantum group SUQ n plus 1, where n is a non-negative integer. You quotient by the subgroup SUQN, and okay, you have to give meaning, of course, to this quotient. It means you have a sister algebra, you have a coaction of a quantum subgroup, and you look at invariant elements. And this is how you define the sphere S2n plus 1 Q. Now, the sphere is denoted by S, not to be confused with the partial isometries in the graph sister algebra. So again, in case this notation is confusing, you just ask me. But whenever there is a Q, a subscript Q, this S probably means sphere and not partial isometry. So here Q is a positive number, is our deformation parameter. The first example in some sense of these spheres comes from Voronovich, because S3Q, this is the quantum space underlying the SUQ2 quantum group. And okay, so when in this original paper, so these things are introduced, are defined as the quantum homogeneous spaces for quantum unitary groups, and but there is an explicit description in terms of generators and relations. So these generators are something similar to a kind of complex coordinates. Is like the realization is similar to the realization of a classical sphere, unit sphere inside. In this case, this is the sphere of dimension 2n plus 1, so inside the complex vector space Cn plus 1. So here I take a Q greater or equal than 0, so the relations, if you write them in the correct way, they make sense also for Q equal to 0. You have 2n plus 2 generators denoted by Zi stars, and this is the universal A of S2n plus 1Q is the universal algebra generated by these elements with some relations. And the relation I only write two just to show you what kind of relation you have. You have several commutation relations. For example, zeta 1, zeta 0 is Q zeta 0, zeta 1. And then you have a relation telling you that this is a unit sphere. You have zeta 0, zeta 0 star plus zeta 1 star plus and so on equal to 1. So telling you that in some sense you are looking at vectors, unit vectors in some sense in this some kind of quantum Euclidean space. Okay, so if n is equal to if n is equal to 0, here should be n greater or equal than 1. If n is equal to 0, you have only one generator. So this algebra is commutative. So all these commutation relations telling you that these generators in general do not commute. You don't have these commutation relations when there is only one generator. And this is simply, for n equal to 0, is simply the algebra of polynomial functions on the circles. Polynomial functions meaning in terms of a Fourier generator, if you want. So if n is greater or equal than 1, so not 2, because I'm using different notations from the paper where I copy-pasted these formulas. So for n, starting from the quantum tree sphere, you can show that these algebras are non-commutative, and two of these algebras associated to different values of the deformation parameter, Q and Q prime, they are isomorphic if and only if Q prime is either Q or Q to the minus 1. So since in particular you can always replace Q by Q to the minus 1, you could take this deformation parameter in the unit interval between 0 and 1, which is what we usually do. Okay, so next.
Let's wait. How about Q equals 0?
Yes, so Q equals 0 is not isomorphic to anything.
Algebraically, but on the level of sister algebras?
Yeah, this is algebraically. I mean, I'm still algebraically. Sister algebras come in a moment.
I know, but now when you go to sister algebras, then Q equals 0 will be the same as Q non-zero, right?
Yes, yes. And the Q will disappear. But here, really, for different values of Q, you get different algebra, non-isomorphic, except if Q and Q prime are one the inverse of the other. That is the only case where you have isomorphism.
Yeah.
Which does not happen if one of the two is 0. I mean, you cannot take the inverse of 0. Okay, so quantum projective spaces were introduced, I think, by Meyer. This is the first paper that I know about it in '95.
Yeah, I think so.
Yeah, and they were introduced as further quotients of these spheres by U1 in some sense. I mean, this is not really the original definition. I think the original definition is again from SUQN plus 1, but then, okay, it's the same. And okay, then 2 years later, Albert Shaw realized that so you have this sphere relation telling you that the star enveloping algebra of these star algebras exists, is well defined, and in fact these are embedded in their star enveloping algebra. You can identify them with dense subalgebras. So what Shaw proved in '97 is that in fact there is some groupoid Gn whose groupoid star algebra is isomorphic to the star algebra of the sphere of dimension 2n plus 1. And this groupoid is independent of the deformation parameter. So this is, I think, the first proof that at the level of star algebras, the deformation parameter does not matter. For Q, this is for Q different from 0 and from 1.
Wait, I just thought that you said that for Q equals 0 it works, so I'm confused.
It works, but it's not in Albert paper. Albert paper is Q different from 0. Then in Hong-Szymanski, they show that both spheres and projective spaces are isomorphic to graph star algebras. And now these here, the deformation parameter can also be 0. Not 1, but 0 is fine. So indeed, Q equal to 0 is fine. It's still independent of Q, even for Q equal to 0, but it was not in Albert paper. This came later.
Okay, yeah, exactly. Thank you.
Okay. Okay, so this is the brief history, but let me show you what are these graphs in particular. These are the graphs in Hong-Szymanski paper. You have your star algebra of 2n minus 1 dimensional now quantum sphere. And in their paper, they construct an explicit equivariant isomorphism with the graph star algebra of the graph that you see in the picture. In the picture, you see the graph with 4 vertices, n is equal to 4. But okay, in general, you have n vertices. At every vertex, you have a loop. And for every vertex, you number the vertices from 1 to n. And for every vertex I, you have an arrow going to the vertex j when j is greater than I. So you have arrow going from left to right. Okay, this is the picture in particular for n equal to 4. Here, the deformation parameter from now on is different from 1. So I'm really looking at the non-commutative case. So in the same paper, they show that there is another isomorphism, but now not a U1 equivariant one, with the graph star algebra of a simpler graph. You have still n vertices, still a loop at every vertex, but only for every vertex, you have only one arrow going to the right, to the next vertex. So this is a kind of line graph plus loops. Okay, then you can pass to fixed point subalgebras. In the first column, this is by definition the star algebra of Cpn minus 1q. And since the first arrow on top is an equivariant isomorphism, it induces an isomorphism between fixed point algebras. And so here you have the core of the graph star algebra on top. In the last column, you can see the core of this second graph star algebra, the one attached to the easier graph. So now the point is that this core, the second arrow on top is not equivariant. So this does not induce a map between cores. So this map, maybe there is an isomorphism, but you cannot just conclude it from the isomorphism on top. Okay, so next point. There is a paper by Ehlers, Ruiz, Sorensen, where they studied these amplified graph star algebras. In Hong-Szymanski paper, they show that this AF core is the star algebra of this amplified graph, which is obtained from the one on top by removing all the loops and replacing every arrow by countably infinitely many. So this amplified graph gives you the core of the star algebra on top. But now, in this paper by Ehlers and collaborators, they show that the star algebra of an amplified graph only depends on its transitive closure. In particular, if you look at this graph on the right, the transitive closure of this graph is exactly this. So these two graphs star algebras are isomorphic. Now, what is this graph? This is exactly the graph that you get from the one on top by removing loops and replacing every arrow by infinitely many. So it is very natural.
Francesco, can you define transitive closure, please?
What, sorry?
Can you define transitive closure?
I will define it, later I will use it for relations. Here I don't want to define it because it's quite tricky for amplified graph. It's not that straightforward. So more or less you can imagine that if you have a relation on a finite set, what is the transitive closure? Is the smallest transitive relation which contains that relation. But when you have infinitely many arrows, is more complicated to define. So if it was only one arrow here instead of infinitely many, and also on the left, that would be the transitive closure in the sense of relations. So I don't want to give the general definition, but we will use this word transitive closure in a much easier context later. So anyway, so it is very natural to conjecture that the graph sister algebra below is the core of the graph sister algebra on top, because the procedure to go from this graph to this is the same as the procedure to go from this graph to this. So it is natural to conjecture this, but still is not a theorem, and there is no way from this picture to conclude this. But okay. So this isomorphism is missing. This will be a consequence of this general theorem that I'm going to explain. So the idea is that, so first of all, let me also observe that the vertical inclusions are in some sense non-commutative principal U1 bundles, meaning that all the sister algebras on top are strongly zeta graded. So you can think of them as describing some kind of total space of a principal U1 bundle over a base space which is described by the amplified graph sister algebra in this case. So we have some kind of U1 bundles, and this is important for us, this picture. So what we want to do is, yes.
Ciao, sono Ludwig, ciao.
Ciao Ludwig.
Can you show yourself on camera, please?
Okay, if it works. No, yes, perfect. Yes. So hopefully. So my question is, why it is not U1 equivariant? I mean, this is gauge U1 actions, no, in both cases.
Yes. Well, because is an explicit formula where you send partial isometries on the right to monomials of degree greater than 1 on the left. So edges on the right become paths of arbitrary length, well, longer than 1. So it's an explicit formula. You can see that you change the grading. You send the things of degree 1 to things that have degree up to n.
Okay.
Yeah, the formula.
Thanks.
Well, it's in the appendix of Onger and Szymanski paper.
You had the example on the previous slides. S goes to Sn.
Well, yeah, I mean, it's analogous to this formula here, but this is for positive sphere going to Teplis. So this is a different, there is a formula for positive sphere going to SUQ2, but that is a different formula. Still, the spirit is similar. Okay. Okay, so what we want to do is now is to generalize this picture as much as possible. So what do I mean? So more or less, it should be clear from this already from these two examples what I want to do. How I want to pass from a finite graph to an amplified graph. But so let me show still one more example, because here we have explicit formulas, and this example includes a Podlish sphere going to SUQ2. So here you have again one amplified graph and the graph which is obtained from the amplified graph by replacing infinitely many arrows by a single arrow and adding loops to all the vertices. So the graph on the right, the graph on the left, this amplified graph, here you have R is a positive integer. You have R plus 1 vertices. One on top, which I call 0, and the other are called 1 to R, and you have infinitely many arrows from the vertex 0 to each one of the vertices on the bottom. So this is the graph of the graph sister algebra describes what we call quantum teardrops or quantum weighted projective spaces with weight 1R. And this is also, this picture here, I think the first time appeared in a paper in 2018 by Brzezinski and Szymanski, while in the original paper where they first described quantum teardrops as graph sister algebras, I think it was a bit more complicated. I'm not completely sure about this, but I took this.
Tomek, what can you comment about it? Tomek?
Yeah.
I don't remember. I cannot comment this.
I don't mean you, I mean Tomek Brzezinski.
Oh, Tomek Brzezinski.
Okay, he's radio silent.
Sorry, no, I was muted. I was struggling to find nice to see you all. Hello, Francesco.
Nice to see you too.
Hi.
Hi.
I'm afraid I cannot comment. So.
Okay.
Okay, so anyway, I think maybe for lens spaces, I think there is in 2003 a first paper of Ang and Szymanski, and then this simplified graph, we usually refer to this 2018 paper of Tomek because it was simplified the graph, I think something like this, if I remember. So this picture is explicitly drawn in this later paper. Okay, so in any case, these are the graph on the left described these quantum teardrops, a special subfamily where the weight is 1r, r a positive integer. If r is equal to 1, what you get is the quantum projective line, or also called the Podlish standard Podlish quantum sphere. And okay, let me denote by EIN the infinitely many arrows going from the vertex 0 to the vertex I. So I tells you the target, and N is the label for these infinitely many arrows. On the right, you see the graph of quantum lens spaces. And if R is equal to 1, so if you have only two vertices, this is SUQ2, or also the Waxman-Seubelman quantum tree sphere. So for R equal to 1, in particular, this embedding that I'm going to write, this isomorphism is between standard Podlish sphere and the AF core of SUQ2, of the graph sister algebra of SUQ2. So here the notation is, this is just for the next formula, to understand the next formula. For the graph on the right, I denote by Lj, the loop at the vertex j, so L0, L1, L2, and so on, and Fi, the arrow from the vertex 0 to the vertex I. So then there is this explicit formula, which tells you send each vertex projection to the obvious one, Pj to Pj, which is not a very good notation, but I hope you understand what you mean. So the vertex projection 0 on the left to the vertex projection 0 on the right, and so on. And then you send the partial isometry of the edge SEIN to this product. You take L0 n times, then move down with the arrow Fi, and then you take Li, the loop Li, n plus 1 time, but you don't take the partial isometry S, but it's a join. And if you count the degrees, you have n plus 1 here, n plus 1 here, but this is of degree minus 1. So you really end in the invariant part of the graph sister algebra on the right, in the core, and you can show explicit that with explicit formulas that this is really an isomorphism with the core. It is injective and surjective onto the core. Okay, so this is an explicit formula. In particular, you have this formula for the CP1Q going to the core of S3Q. But already for projective spaces of dimension greater than 1, complex dimension greater than 1, we could not write down an explicit formula. So already CP2Q, we could not write down any explicit formula. Then, okay, so what is the general construction? So forget about explicit formulas. What is the theorem, the general construction, the general theorem, and how we prove it? So the idea now is the following. So we are interested in non-commutative principal U1 bundles, compact non-commutative principal U1 bundles, which means extensions of this form. We have a graph sister algebra sister of E, and this is the total space of the bundle, and the base space is described by the core of this graph sister algebra. So principal U1 bundle means that C star of E we want it to be strongly graded. Compact means that we want a unital C star algebra. And there is a theorem saying that a graph C star algebra is unital and strongly Z-graded if and only if the graph is finite with no sinks. So this tells us what kind of graph we should consider. This E should be finite with no sinks. Next, we want to find an amplified graph F such that C star of F is isomorphic to the core of C star of E. But when E is finite with no sinks, we know that the core is an AF algebra. So C star of F, in order for this to work, also C star of F should be an AF algebra. And then there is another theorem saying that C star of F is an AF algebra if and only if the graph F is acyclic. There has no directed cycles. So this is our condition on F.
Sorry, Francesco, I'm about confused why you want E to be unital. How about O infinity Cuntz-Krieger algebra?
Well, I want it to be unital because I like a compact quantum spaces.
No, I like to be unital, but unital means finitely many vertices, not finite graph.
Yeah, but finite graph comes from the condition of strongly Z-graded. So
again,
when you have
why?
a finite... Sorry?
Again, why? I mean, when I have gauge action on the infinite Kuntz algebra, it's not free.
No, okay, the theorem is take a graph with finitely many vertices.
Okay, fine.
So unital graph C star algebra. This is strongly Z-graded. This is strongly Z-graded if and only if the graph is finite with no sinks.
Right. And if this
so strong grading tell you that also E1 should be finite. If E0 is finite, this is the unital version. Then for non-unital algebras, you can have a strong grading with more complicated conditions.
Yeah, sure. But I'm happy with unital. But I still don't see how. I mean, I understand no sinks because I remember how it works, how the proof goes. And Vetepti's graph is an immediate counterexample to the freeness of a gauge action. Okay. But I'm really surprised.
Tepli says a sink.
Yeah, exactly. This is why it's obvious to me why you have no sinks. Okay.
Yeah.
But I completely don't understand this finiteness of a graph. I mean, finite E1. How does strong grading? How can strong grading enforce on you that you have finitely many edges? Which I don't understand.
Well, it's not obvious, but I mean, you have to dig into these theorems. It's not obvious, but it would be not easy to explain now. It would take quite a lot of time. Basically, what you get is the graph that the graph is rho finite and then finite. You have no infinite emitters. You have no sinks. So every vertex is irregular since you have a finite. So rho finite graph with E0 finite is just finite.
Yes, of course.
But it's not. I mean, it's not something obvious. It's not that you just look at this theorem and you understand why. And in the non-unital cases, even to formulate this condition is complicated.
Yeah.
Okay, so anyway, so let me go on. This is just a motivation to explain that more or less the next theorem is the most general thing we can hope for. So here R is a finite acyclic graph with no multiple edges. So between two vertices, there is at most one edge. So from this R, you construct E by adding a loop at every vertex. And again, from this R, you construct F by replacing each edge by infinitely many, countably infinitely many. So now E, since R is finite, E is finite. And since E has a loop at every vertex, E has no sinks. Since R is acyclic, F is acyclic. And then the only thing that I should motivate is why I need no parallel edges. So under this condition, if I construct E and F in this way, whatever is R, if these conditions are satisfied, then this isomorphism holds. C star of F is isomorphic to the core of C star of E. So the only thing is why no parallel edges. I'll try to explain why it is. So first of all, how it is proved. We could not find an explicit formula, but you can prove it by computing the dimension groups of these two sister algebras. And this, I think, is in any case is interesting for itself, because it's not that you have a lot of explicit computations of dimension groups. And I'm going to show some explicit expression for dimension groups soon. So this is how you compute. Now suppose that R has no multiple edges. So this means, so source and target map, the Cartesian product is injective, and you can think of R1 as a subset of R0 cross R0. So R1 in this case is a relation on the set of vertices. And a relation as a graph is a cyclic if and only if the transitive closure is a partial order. So the point of this last condition, having a relation instead of an arbitrary graph, the point of this condition is that then acyclic means that we get a partial order, and the partial order is what then gives you the dimension group. This is a partial order on vertices, but then it becomes a partial order on vertex projections, and is what allows basically the computation of the dimension group. I mean, it's not really a full explanation, but this kind of some kind of motivation to convince you that there is a reason why we put also this condition of no parallel edges. Okay, so last remark that I want to say is that since C star of E is a finite graph with at most one arrow between two vertices, and this graph has no sinks and no sources, this is what we call, C star of E is what we call a Cuntz-Krieger algebra. So this is the C star algebra of a 0-1 matrix, a finite 0-1 matrix with no zero rows and no zero columns. And this is just to explain why there is this other keyword, Cuntz-Krieger algebra, in the title of the talk and of the preprint. Okay, so this is the theorem. Let's go back. So projective spaces, quantum projective spaces are a special case. Quantum teardrops are a special case. I will show one more example, but let's go back to projective spaces again for a moment. So we know classically what is the case theory of Cpn-1. This is a ring, the ring of truncated polynomials in X, where X is some explicit element in K theory, is the Euler class of the dual of the tautological line band. So this is the K theory of Cpn-1. Now, the dimension group consists of K0. In all these examples, K1 is 0. The dimension group is well defined for unital, stably finite C-star algebras. Both commutative C-star algebras and AF algebras are stably finite. And now this is the commutative case. So the dimension group consists of K0, the positive con, and the class of the unit. The class of the unit is always obvious what it is. For graph C-star algebras is the sum of vertex projections, so I'm going to omit it, but the positive con is not obvious. So in the case of classical projective space, the positive con, you can prove that it is contained in the following set. The set on the right-hand side contains 0 and contains is the set of all truncated polynomials such that A0 is strictly positive. So the constant term is strictly positive. So what you can prove is that there is this set inclusion. Now, if n is equal to 2, so if you have a CP1, this inclusion is actually an equality, and you have an explicit computation of the positive con. But if n is greater or equal than 3, this inclusion is proper. You can prove that there is some polynomial on the right which does not belong to the positive con. Now, I tried to find in the literature some explicit computation of the positive con for projective spaces, but I could not find it. So this is something that we computed. But even in the classical case, in dimension greater than 1, the computation is not completely explicit. You only have some set inclusion, not an equality. This set inclusion, on the other hand, is all what we need. So now quantum case. In the quantum case, K0 of Cpn-1Q, this is a free group on n generators, and these n generators are the classes of the vertex projections. So every element in K0 is a sum, an integer combination of these classes, A1, P1, plus A2, P2, plus AN, Pn, where A1, A2, AN are integers. And when does an element like this belong to the positive cone? You can prove that the positive cone consists of all the combinations such that the first non-zero coefficient from the left is positive, if there is one. So you have both zero, the class of zero, and for non-zero elements, the first coefficient, non-zero coefficient from the left should be positive. So here you see that the quantum case is actually easier than the classical case, because in the quantum case you can explicitly compute the positive cone. And with these two propositions, a corollary is that you can prove that the dimension groups of CPN and of CPNQ, they are not isomorphic. So K0 in both cases as an abelian group is zeta to the power n. So they have isomorphic K0 groups. CPN-1 and CPN-1Q have isomorphic K0 groups, but non-isomorphic dimension groups. And this is, you can prove it by contradiction. You assume that there exists an isomorphism of abelian groups which maps one positive cone to other one, which maps the class of the unit to the class of the unit, and you show that you get some contradiction. Okay, so this is, in some sense, a small result, but I think is an interesting result. Okay, so let me show now the main example, the example we were interested in, and that in some sense, this is the other motivating example for this whole general theory. This is quantum Grassmannian. So it was proved in a paper, again, a paper of Brzezinski and collaborators, a paper in preparation. I don't know, Tomek Brzezinski, I don't know if you have updates about this paper. But
no updates, I'm afraid. No
updates. But there is, I found then Karen told me that there is, she has some proceeding where these results are announced. So there is something written already.
Yes, it's in, I think it's in Oberwolbach proceedings.
And okay, in any case, so we know from other people's results, but we believe them, that this Grassmannian GRQ24 that Elmar talked about last week. This you can define again, starting from quantum unitary groups as a quantum homogeneous space. So in terms of generators, some kind of coordinates and so on. But then you can prove that it is a graph C-star algebra. And it is the graph C-star algebra of an amplified graph. This is the graph that you can see in the picture. And this graph, the way you obtain this graph, there is a general recipe for all quantum flag manifolds. And the idea is that you start from the Weil group and some coset space. On this coset space, you have a partial order, and this partial order is really up to replacing a single arrow by infinitely many. This is the graph that you can see. Okay, in any case, also in our preprint, we recall this construction. We repeat basically what is explained in Karen proceeding. So this is the graph described in GRQ24. Now, our general theorem tells us, okay, this graph C-star algebra is the AF core of the C-star algebra of the graph that you see below. Infinitely many arrows become a single one, and then you attach a loop to every vertex. So you have your non-commutative U1 principal bundle over the Grassmannian. So what I want to do is basically I want to use this bundle, in particular the total space of this bundle. I want to use it to give you a decomposition of the C-star algebra of the Grassmannian. Now, this decomposition, I have to say that it is possible that the same decomposition you can get from the amplified graph, but I'm more comfortable with finite graphs. And this is what we did also for projective spaces with Piotr, Mariusz, Tobolsky, and Francesca Ricci. So to give a CW complex decomposition of the quantum projective space, what we do is really we use the graph of the sphere on top. So this is something analogous in some sense. I prefer to use this graph because it's finite, but okay, maybe it's not needed. Maybe the same result you can get from the graph on top. So anyway, but the first thing I want to do is, okay, this graph is nice, but from this graph you cannot recognize anything related to spheres or any balls or anything familiar. On the other hand, you can change this graph. What you can do is you can add edges. Whenever between two vertices there is a path, if there is a path, you add an edge. And if you do this, you get this graph here. Now, this graph here is very similar to the graph of a quantum sphere, of an 11-dimensional quantum sphere. You see that the only difference is that there is this red arrow that you see in the picture from vertex 3 to vertex 4 here is missing. So if you add the red arrow, you get S11Q, the 11-dimensional quantum sphere. And without this arrow, you have this total space of principal U1 bundle over the Grassmannian. So the Grassmannian is the core of this graph sister algebra. Okay, at least we see that is not very far from something we are familiar with. And so removing one arrow, basically what you do when you remove one arrow, in some sense, something becomes zero. You get some relation. This is explained in the preprint, but it's not a very precise statement. So in some sense, you get one extra relation, which is kind of a Q to zero limit of Plucker relation. It has a geometrical meaning of this relation, but is not completely, I mean, okay, so let's see. So, sorry, there is a silence. Okay. Okay, so let me explain why this is interesting, this connection with the 11-dimensional quantum sphere. So classically, you can think of the 11 sphere as unit sphere in C6, where the component of a vector in C6 have denoted for some reason by x13, 12, 13, 14, 23, 24, 34. And I use this notation. This is a vector of norm 1. I use this notation because then you can write a Plucker equation in a familiar way as x12, x34 minus x13, x24 plus x14, x23 equal to 0. So what is this relation? This defines a quadric in CP5, which is the image of, basically is isomorphic to your Grassmannian, and it defines also a quadric in S11, and the quadric on S11 is the total space of this bundle classically. So classically, this total space is described by a sister algebra, which is a quotient of the sister algebra of S11, of the 11-dimensional sphere. In the quantum case, this is not true. You don't get a quotient of the algebra of S11Q, because basically when you remove this arrow from the sister algebra of S11Q, so this is in some sense not an admissible operation on this graph. You don't get, it does not induce in any obvious way a star homomorphism, but okay. Okay, so this was just a comment to relate this construction with the classical case. Okay, so now CW structure. So we want to use the description of the sister algebra of this quantum Grassmannian, the description as AF core of some bigger graph sister algebra to derive a decomposition of this sister algebra. And now here I'm calling a kind of CW structure. We will see why it is not completely appropriate to call it a CW structure, not even a non-commutative version of a CW structure. So classically, how can you get the Grassmannian to 4? You start from a point. To this point, you attach a disk along its boundary, and you get CP1, which is a two-sphere. Then you attach two four-dimensional cells, so two four-dimensional closed balls along their boundary, and you attach them in such a way that what you get, the next skeleton, is two copies of CP2 glued along CP1, where CP1 is embedded in a standard way inside the CP2. To this,
and what is X6?
Sorry?
What is X6?
Yeah, okay. So now I'm going to tell you, to this four skeleton, you attack a single 6-dimensional cell and you get something which I denote X6. To this X6, you attach one 8-dimensional cell and you get the Grassmannian. So what is X6? Well, I mean, in the quantum case, it's just some sister algebra. In the classical case, it has a description as points in the Grassmannian you can think as two-dimensional complex subspaces of C to the power 4. And X6 is the collection of all the subspaces whose intersection with a fixed subspace has a dimension at least 1. So it has something to do with it, is the collection of points in the Grassmannian which intersect something in an appropriate way. So there is a geometric description, but is it in the classical case, in the quantum case? At least for now, we don't have it. But so the first thing that we do, okay, so let's put C everywhere and reverse all the arrows. So all these embeddings from the dual algebraic point of view become quotient maps between C-star algebras. So this is the picture that we want to generalize to the quantum case. And I should explain also what I mean now by gluing. So now by gluing X and Y along some topological space zeta. So what do I mean? X, zeta, and Y are topological spaces. You have two maps, continuous maps, zeta to X and zeta to Y. So by gluing, we mean that this space is by definition the push out of these two maps, which from a dual point of view becomes a pullback of C-star algebras. So if you want, one way to define the C-star algebra of this X glued to Y is as a pullback of the two star homomorphism, C-star X to C-star Y and C-star zeta to C-star Y. So you have this kind of pullback diagram. Yes?
Set should be down. Set should be down.
Which set?
Set is the one you
yes, in this picture, zeta and Y are exchanged. Sorry, this is a typo. This is Y and the one below is zeta. And you glue X and...
Bravo, Elmar.
Yeah. Yeah. Sorry, I have to remember then to correct all these typos before I send the...
Revenge is sweet, isn't it? Revenge is sweet.
Yeah.
Because a week ago it was Francesco finding errors in Elmar.
Yeah. Okay, so anyway, so by gluing now in the non-commutative words, so by gluing quantum spaces, we mean this. We gluing two spaces along a quantum subspace means taking a pullback of suitable star homomorphisms. So what you have is a commutative diagrams of C-star algebras like the one in the pictures. And pi1 and pi2 are some star homomorphisms. And if A is the pullback of these two star homomorphisms, we interpret this as gluing A1 and A2 along A12. So concretely, I mean, pullback means that this diagram should have some universal properties, but for C-star algebra, okay, you can take the next one as a definition. It's not really a definition of pullback, but so A up to isomorphism, you can imagine that A is given by the set of pairs A1 and A2 in the A1 direct sum A2, such that these two elements have the same image in A12. So this is concretely our gluing, our quantum space obtained by gluing A1 and A2. Okay, so next, in particular, I want to glue quantum cells. What does it mean? So classically, attaching a cell means the following. If X minus 1 and XK are two topological spaces, saying that XK is obtained from XK minus 1 by attaching a d-dimensional cell means that you have a pullback diagram like this, where here you have XK, here XK minus 1, here you have a ball of dimension d, where d is the dimension of XK, and below you have a sphere of dimension d minus 1. One arrow here is the restriction of functions on the ball to the boundary, to its boundary sphere. So this is BD is a closed ball here. Okay, so this is what it means attaching one cell. This is how you pass in a CW complex, in a CW structure, you pass from a skeleton to the next one. Then, okay, so the idea in the quantum case is that we would like something like similar to this. We would like a sequence. So a sequence of quotient maps like this, where at each step you pass from a C-star algebra to the next by a pullback like this, where on the bottom you have something which is a kind of quantum ball going to a quantum sphere. So it's a kind of non-commutative boundary map from a quantum ball to a quantum sphere. Now it is debatable what we mean by quantum ball and quantum sphere. The minimal requirement would be that at least the case theory is the correct one, is what you would expect. And we will see that this is actually the problem with our example. We still not completely clear how to solve it. So what do we have in the case of the Grassmannian, quantum Grassmannian? So the result is the following one. You can prove using this presentation as core of a graph-system algebra. You can prove that there is a quotient map from the sister algebra of the Grassmannian to 4 to some sister algebra that denote by C of X6Q. Now, what is this X6Q? Maybe I can tell you immediately what it is. This is, let me move on. This is, you take the graph, this graph here, G1, which is obtained from the graph of the bundle of the Grassmannian by removing one loop. So what I'm doing is I'm using a theorem from my paper with Francesca, Piotr, and Mariusz about trimmable graph-sister algebras. And from this total space, I kill this loop. If I do this, the core of this graph-sister algebra, this is what I denote by X6. This is the first step in our decomposition. Here you get the core. So you repeat the same thing. So the next thing is that you get a second graph G2 by removing all the arrows going to this sink. And then here you remove one loop again, this trimmable edge. And you get this graph which I denote by G3 with one sink. Again, from this general theorem, this paper with Piotr, this G3, you have now a quotient map of sister algebras from C of X6Q to the core of this G3. And the core of this G3, you can prove that is just the gluing to copy of CP2Q over CP1Q. I will give you some more detail about this in a second. So this is the next sister algebra that you find in this sequence of quotient maps. Then you have CP1Q, and then you have complex numbers. So you have a sequence of quotient maps, but it's not just any sequence. Now it's very close to what we would call a CW structure, because this first quotient map is the top arrow of a commutative diagram, which is a pullback diagram. And on bottom, you see that you have a quantum to ball and the circle. And this arrow is the boundary map from this quantum ball to the circle. So here in this first step, you are taking this ball. This is just Toeplitz operators. You take this ball and you attach to a point along its boundary, and you get CP1Q. So the second arrow also is a very nice one. It has a geometric interpretation. What is this arrow? We have a commutative diagram. Now the diagram number 2 in this picture. In this commutative diagram, what you do is you have two squares that you can see here. The first square, both squares are pullback diagrams. In the first square, you have a CP1Q, this here. Below, you have S3Q and the 4-dimensional quantum ball. And so this means that you are gluing a cell, this quantum ball, to CP1Q. And what you get, you can show that it is CP2Q. You repeat this again, you attach another quantum ball to CP2Q along its boundary. And what you get is this sister algebra. So the quotient map that you see in this decomposition, this quotient map here, makes this whole diagram commutative. It's the composition of these two quotient maps. So you can interpret it as attaching two balls, one after the other. If you look at our preprint with Sophie, in fact, you can give also a different interpretation. Instead of attaching one ball after the other, you can present this as a multi-pullback, where you glue the two balls at the same time to CP1. So if you like this picture more, it is equivalent. Okay, so this is the second step. In the third step, so this arrow here from the 6th skeleton to the 4th skeleton, this arrow is also the top arrow of a pullback diagram. So we are still gluing something. What we are gluing is the graphs. Here we have the graph sister algebra of G3. Here the graph sister algebra of G4. These G3 and G4 are graphs. I will show them in a second again. The graphs that you obtain by this trimming procedure, by eliminating the trimmable edges, whatever it means.
Francesco,
yeah.
Francesco, I understand that diagram, pullback diagram number 3 defines X6Q, but is it a graph sister algebra or not?
X6Q is the core of a graph sister algebra. Because what we use here, we use our trimmable theorem, but we pass to fixed point algebras, the one where you pass to fixed point algebra. So on top you have cores of graph sister algebras, and on the bottom you have graph sister algebras. So I don't know if this core is also a graph sister algebra. Maybe I should check the next picture to tell you if our theorem applies, but maybe I can tell you in a second. I will check the picture and
okay.
So from the sixth skeleton to the Grassmann, you have something similar. You are attaching something, it is still a pullback diagram. You are gluing something that you describe in terms of graphs. So now the problem here is that these graph sister algebra, they have the wrong K-theory. And so they don't have, G1 and G3 should have the K-theory of a ball. So K0 should be zeta and K1 should be 0. Instead, we get zeta square and zeta. You have one extra zeta, both at degree 0 and 1. G2 and G4, the K-theory should be that of an odd-dimensional sphere, which means that K0 should be zeta and K1 should be zeta, and instead we get zeta square and zeta square. Now, this means that in particular, these last two arrows we cannot really interpret as a skeleton in a CW, strict CW complex structure, like we defined it in our paper with Tomek, Bartek, and Albert. So here, these are not boundary maps from a K-sphere to a K-ball in our language. But I don't think this is a big problem, because what I think is that what is on top is correct. The arrow on top is part of this pullback diagram. But I think that, okay, of course, the pullback diagram is not unique. I think you can fix it, changing what is below, to get also something with the correct K-theory. So I think you can fix it, but still I don't know how to do it. So in any case, so these are not the diagrams that you would interpret as attaching cells. You're attaching something else. But that does not mean that you don't get GR to 4 from X6 by attaching one cell. Maybe there is a different pullback diagram where the top arrow is the same arrow, and on the bottom you have the correct things. So this is what I believe, but it's something we are trying with Elmar to solve this, but not using graph sister algebras, so in a completely different framework. And with graph sister algebras, I don't know, we'll see if there are news later on. Okay, let me show you just 1 second the graph again. So X6Q, yes, so X6Q is the core of G2 of this graph here. So in particular, our theorem applies, because if you remove the loops, you have a finite cyclic graph with no multiple edges. So in particular, this core is indeed an amplified graph sister algebra. It is an amplified graph sister algebra where the amplified graph is given by this here, where you remove the loops and you replace each arrow by infinitely many. So here, for this decomposition, the only thing that we use, in fact, is this theorem about trimmable graph sister algebras. This is why I like this presentation. Oh, sorry, 1 second. Is not working. So let me attach this here and see if this is working. Sorry, 1 second. Otherwise, my computer will be dead soon. Yes, now it's working. Okay, so this is why I like the description of the Grassmannian as core of something, because then for this kind of CW structure, we only need this theorem about the trimmability of graph sister algebras. And we take this theorem and we use it like 5 or 6 times, basically. This is what we do. And but there is another theorem that I want to mention that we use, because at some point, as a 4 skeleton, what you get as a 4 skeleton at some point is this guy here, the core of this graph G4, the AF core of this graph G4. And now there is another theorem that allows to interpret as this core as gluing 2 quantum projective spaces. And this is the second ingredient in the proof that is about admissible decompositions. So the one on top is the graph G4. Inside this graph G4, you have 2 subgraphs. One obtained by killing the last vertex and all the arrows that start or end at this vertex. This is the graph on the left. But you can also kill the third vertex and all the arrows going to this vertex, and you get the graph on the right. The union of these two graphs is the one on top, is the G4. And what is the intersection? The intersection is the graph which contains the first two vertices, the two loops, and the arrow from vertex 1 to vertex 2. This is, I mean, there is a general theorem in a paper by Piotr Sararezhnikov and Mariusz Tobolski, saying that under suitable condition, this is push-out diagram of graphs dualizes to a pullback diagram of graph sister algebras, and you can pass also to cores. In fact, it is a U1 invariant pullback diagram. And what is this pullback diagram? Well, so on top, we get the AF core of G4, which is the 4 skeleton. On the left, this is the graph of the quantum 5 sphere, which becomes the core is CP2Q. On the right is the same. I mean, the picture is a little bit different, but you can see that left and right, these are the same graph. So on the right, you have another copy of CP2Q. And on the bottom, you have the core of SUQ2, which is the CP1Q. So what we are doing...
Wait. How come SUQ2 is CP1Q? What are you talking about? CP1Q is a 2-sphere.
Yes, I know. No, what I'm saying is I take your pullback diagram and I pass to...
You go to the core, okay.
I always go to the core. Yeah. And I can do it because it is a pullback diagram of U1 sister algebras. So you go to the core everywhere. Here you have the core of sister G4. On the left, you have CP2Q. On the right, you have CP2Q. And in the bottom, you have CP1Q. So the thing on top, which is our 4 skeleton, thanks to this theorem about admissible decompositions, this 4 skeleton, you can see that is isomorphic to the sister algebra of this guy here. We are gluing 2 copies of CP2Q along CP1Q. It would be nice to have a geometric interpretation also for the 6 skeleton, but we don't have it. And it would also be nice, let me show you the general theorem again, and then this is the end. And it would be nice. So what is missing is it would be nice to have a geometric interpretation for this. And it would be nice here to modify these pullback diagrams so that you get the correct K-theory. But I mean, in any case, this was, this was just an example of application of a general theorem. So the main point of the preprint is this general theorem, which I think is quite useful. I mean, something that is very natural to guess, but then you want to prove, of course. Okay.
In the classical case, what is this X6? You
yes,
said it,
so,
say it again.
Yeah, so X6, the Grassmannian, you think of the Grassmannian, a point in the Grassmannian is a 2-dimensional vector subspace in C4, where, I mean, 2-dimensional in the complex sense.
Yes.
So you have planes, not really planes, because the real dimension is 4, but let's say that you have planes in C4, in the complex sense. You fix one of these planes, and then you look at all the planes whose intersection with this one as dimension at least 1, which means either it's 1 or 2. And these are the points in the 6 skeleton.
Okay.
But I mean, in the quantum case, to give an analogous description, it's not, at least with graph sister algebras, it's not something very obvious how to have this description. Okay, so this is the end actually of my talk. So I think if there are more questions, now is a good point to start asking questions.
Okay, grazie mille to begin with.
Thank you.
Grazie.
Yes, Tommy.
Okay.
No, he's uploading.
No, this is clapping. Now let me enjoy myself first. So for starters, at the very beginning, you were showing some morphisms of graphs which were not preserving the length. So are these path homomorphisms in our sense with Mariusz Tobolski?
So this is comes from covariant induction.
Okay, that's super.
And
Okay.
this is the one, I think that this is exactly the one that you have in one of your papers, is written there, I think.
That is true, but you also mentioned some other one.
Okay, this one does not go into the core. And the image is a Teplitz operator. This is from the sphere to the disk, not from the sphere to SUQ2. Now, from the sphere to SUQ2, you have this one. So now take R equal to 1, so only two vertices. Now you go from the sphere, published sphere, to the core of SUQ2. And this is not a covariant induction. It's covariant induction with extended graph, because you take one arrow on the left, you send it to n loops, you go down, and then n plus 1 loops in the extended graph, in the wrong direction.
Francesco, so wouldn't it be what we are doing right now with Gilles and Marius about these inverse semigroups? The new category?
Well, it is possible. It could be a special case of that construction.
Wonderful. Okay, that's very cool.
But this is very similar. Okay, this is something that for CP1, well, I don't remember for CP1, but for quantum length spaces, this is very similar to a formula which is in the paper of Brzezinski and Szymanski. In the proof of a theorem, they have a formula where they construct an embedding. Well, it's not exactly this, but you can, from their formula, you can get this with some work. So, I mean, is not. I just want to say this is not really an original result. In some sense, you can get from their formula, which looks quite similar, even if there is a different sister algebra involved. But it's also something that you check explicitly, so it's not something very difficult to check that it works.
Okay, now can you go back to your last slides, please?
Yes.
No, not the end. Okay. By the way, why do you say that this is a story of incomplete spheres? What's incomplete about spheres? You started your talk by saying incomplete story of spheres, of quantum spheres.
Well, I mean, no. The history. I give an incomplete history, meaning that not everybody who worked on this is mentioned here. A lot of people who worked on spheres.
Okay.
But the result is complete. Maybe it's not the best possible result, but the proof of the result explained are complete proofs.
Okay, could you now go back to the last, I want to see the graphs. Next slide. To next, I want to see this push out. Yes. So now if we go to the core, all right, will it still be a push-out diagram in our sense? I guess it will be, right?
So you mean if you reply everything by amplified graphs, you mean?
Yes, exactly, yes.
Yeah, I think it should be.
Because here it's very simple. You always do the obvious recipe. You kill a given vertex and all arrows ending in there. And if you have infinitely many arrows ending in there, so be it. You kill infinitely many arrows. So I believe you also have a push out at the level of CP, gluing CP2s over CP1. It's also a push out of graphs. Yeah. Okay, which means
should work with cores. The reason why I used these graphs instead of the amplified ones is because then I don't know what to use instead of trimmability for the decomposition. If I start with the amplified graph instead of the core of the non-amplified one, what do I use instead of trimmability? So the starting graph, let's say that you start with this graph here.
Yes.
If I use the one below, I can trim the last loop. But if I use the amplified one, how can I explain that there is something that is... because you have this, for Polish, you have this mixed pullback diagram, right? Where you have...
that's true, yes.
Yeah, but in that case, you use a theorem where you assume that you have some map, that you know some map that exists. And in general, we don't know that this map exists. That's the point, from the amplified to some other graph sister algebra. Because I tried to think if I could do something similar here, so with this mixed pullback. But
yeah, I agree. It's more complicated. With mixed pullback, it's more complicated. You have more conditions, but a theorem we have in our most recent paper is quite general about these type of graphy inductions, okay, of pullback diagrams. But I was thinking about this equivariant case when you go to the core, and because if you go back again to the last slide, my point is that this allows you to see that this fixed point sister algebra is again, this core sister algebra is again a graph sister algebra. This,
yes.
You know it because you have a push-out graph which is obtained here. So I don't know about X6, but this, if you want gluing or if you want fixed points, which is one and the same thing, is a graph sister algebra, and you know how to draw the graph because there's a push-out graph.
But Piotr, the only thing is that this picture that you see, this is only to show that the skeleton is really CP2 union CP2, but this is not the picture which you interpret as gluing a cell. This is not. Here you don't have boundary map from a ball to sphere, so this is not the pullback that tells you that you are attaching a cell. So this is some independent result to give an interpretation to the four skeleton, which you can do also with amplified graphs in this case. Because from the trimmable theorem, you get that the core of the graph on top is the four skeleton. This comes from trimmability. But in this trimmable theorem is a different pullback diagram. Then I write down this pullback diagram just to show that there is a geometric interpretation to this four skeleton, but it's something independent.
Yeah, fine, but forget trimmable for a while. Are these arrows just the natural inclusions of subgraphs?
Yes.
So what I just said stands.
Yeah, this is correct. Yes, you can replace everything by amplified graphs describing the cores, and that is also a pullback diagram.
Yeah, and then you have a nice amplified graph, which will be the graph of the graph C-star algebra, which is the U1 fixed point of C-star G4.
Yeah, but this comes also from our general theorem that the core of this is the amplified graph C-star algebra where you remove all the loops and arrows.
Okay.
Yeah, this is the consequence. All these graphs, to all these graphs, you can apply our theorem because they are Cuntz-Krieger algebras.
Okay, one last question from me. But it's a silly question. I'm wondering what happens if in these amplified graphs you would use uncountably many edges, not countably many edges. So imagine something like Podlesh, but uncountably many edges. Because it's not clear for me that you would have it as the core of some other graph system.
Well, I mean, but here is always countably many, so I don't know. If it is uncountably, well, it depends on how much uncountable, say like real numbers, a continuous family of arrows, but I don't know what
Exactly.
I have no idea.
Yeah.
Maybe
okay, that's all from me.
Wait. Piotr, maybe Atul knows the answer.
Maybe
Atul, yes.
Yeah.
But you have to come closer.
Maybe it has some topology or something. Maybe that can help probably.
So it could be a topological graph sister algebra, he says. Something.
This is a very interesting thing. Okay. Okay, I really like this answer. Okay. Because obviously we can do infinitely, uncountably many arrows, and it's a different sister algebra, of course. I mean, compact operators on a separable, non-separable Hilbert space are different animals, I believe. But now, I would like to see, this as the core sister algebra of some graph sister algebra, and yeah, I really like that it can be the topological graph sister algebra. Okay, thank you so much, Atul. Tomek.
Okay, so if you could give me some white place to write something.
Yes,
The
I
end,
think
the
you can
last
open
slide.
more.
I need more. I need more.
Go to the end. You have this last slide.
Go to the end. Yes.
Ah,
Yes.
okay, sure.
Thank you. Thank you. Okay. So, how could I write on this?
Like this.
Yes.
But I see only what
Could you allow
Piotr
me?
is writing.
Could you allow me to write on this whiteboard?
Well, I'm allowing you.
Aha.
It's Francesco's whiteboard, not mine.
Okay.
So, yeah, you have to click on a button on the menu, and then you can write.
Yes. CIA, yes.
Yeah. And now,
I cannot find this annotation.
well, if you see where is the sharing button, two buttons to the right.
So these are tools of
Zoom.
not of Zoom, of you, Piotr.
No.
These are your. They are tools of this person running the seminar at the moment.
No, I mean, everybody should have a little pen on the left-hand side when somebody shares the screen, and you click on this little pen, tools appear, and you can write. Okay, Tomer, can you write or not? Because I don't want to wait 5 minutes till you figure it out.
So could you come back, Francesco, could you come back to your diagram with infinite number of arrows? It's a diagram from this Grassmannian G24.
Yes.
Yes. Okay. So look, if you look at these vertices,
yes,
you could think about the first vertex as a point, the second vertex as CP1,
yeah,
next two as copies of CP2,
yeah,
next one as X6, and the last one as G42.
Yes.
Okay, so this diagram looks exactly like diagrams coming from the Brillouin order, from the order of U1 orbits.
Yeah, that's how it's constructed in this general theorem. It works for every quantum flag manifold. That's how you construct the graph.
Yes. So this Brillouin order, which is in fact corresponds to this CW structure by Schubert variety. This corresponds to some order on the level of the Coxeter group.
Yeah. Yes.
Okay. So this is another combinatorics which is behind this picture, and I wonder how this combinatorics is related to the combinatorics of this graph.
Well, in the case of graphs, these vertices tells you what are the invariant ideals in this graph sister algebra in the bottom. So that's how you construct the quotient maps. You have several ideals.
Okay, so everything comes from the gauge extent of U1.
Yeah. And you have a classification of ideals, of invariant ideals, and the combinatorics is the same as the Brouhat order or even the symplectic, the decomposition in symplectic leaves, I think.
Okay.
For some canonical symplectic Poisson structure. So there are various interpretations of the same combinatorics. For graph sister algebras, they classify ideals, invariant ideals.
Yes. Okay, so this means that this classical combinatorics is very robust. It survives this quantization. Okay.
Yeah.
So now my real question. If you take Q equal to 0,
Yeah.
you have another type of combinatorics which is related to crystalline bases.
Yeah.
Okay, so I wonder what is the relation between this Bria order and these crystalline bases?
Well, I'm sure that there is a relation because the graph sister algebra basically is the generators that you use and representations are those that you get for Q equal to 0, basically, in some sense. So in some sense, we are working at Q equal to 0. And there should be some relation, I'm sure, between the crystal bases and these ideals, some concrete relation that one can write down. Maybe is how from you pass from one algebra to, I don't know. Well, I don't want to say something wrong, but I'm sure that if one sees the formulas, there should be some very explicit concrete relations. Yeah.
But you don't know any paper about this?
Well, I know which paper you are talking about, but I don't know it well enough to comment.
Okay.
Yeah.
Okay. Okay, thank you.
All right. Anybody else? Adam.
No, I'm happy. Very
Why
nice
are you
talk.
always
Thank you.
Anybody else? From Morelia, maybe. Elmar, Atul.
I don't have questions, thanks. I can ask directly, Francesco. We will talk about it. It's this week.
Okay. Okay. All right. Anybody from the Zoom? If nobody from the room. Anybody going twice? Anybody going twice? And thank our speaker again. Thank you. Now I stop recording.